Welcome to another podcast. In this episode, we're going to be taking a look at how to construct a solution using series solution method. Now, the example that I'm going to look at right here is an example that we could easily handle without series solutions, but given that it's sort of our first approach to series solutions, it might be nice to look at a model that we already know the answer to. And this is such a model. We're looking at y double prime plus y equal to 0. It has a characteristic equation, r squared plus 1 equal to 0. So we know the characteristic roots are plus or minus I, which means that our solution is going to be a c1 cosine x plus c2 sine x. Now, that's all well and good. Can we apply the series solution expansion method to this and come up with the exact same answer? Because if we're getting a different answer, then this is probably not going to be the right kind of method for us. So let's make sure that we all understand what we're doing for the series solution, for the series expansion method. The idea is basically I'm going to take the equation and I'm going to suggest that a possible solution be a power series expansion. In other words, I'm basically making a huge guess. I'm basically saying, okay, I know that power series, they can represent any function with certain properties like continuous derivatives of all orders. We can use like a Taylor series approximation, for example. I know they can approximate just about anything, so why don't I just assume that the solution is this power series, and then all I have to do is basically figure out what the ANs are. So our goal in this process is to figure out a formula for the coefficients, the ANs. Now, that's sort of easier said than done. It can only be done well in a few cases, and we're going to look at those cases in particular because they are extremely important. But even when it can't be done, it at least gives us nice approximations for solutions. And as we've seen in other courses, approximations can go a long way. Looking at things like Simpson's rule, we did Euler's method and Runge-Kutta earlier this semester. So there's room for even this method, even if we don't recognize the formula for the ANs we wind up with. And we're going to take a look at that example for the second video, but this one we're going to wind up hopefully with cosine and sine expansions that we recognize. Now there's one thing I want to talk about here. I'm expanding this about the point 0, so we would call this a Maclaurin series expansion or a power series expansion about the point 0. The reason that I am able to do this is because 0 is an ordinary point. So x of 0 equal to 0 is an ordinary point for this particular equation. I would need to check that. Go back and look at the video on singular and ordinary points if you need to. But basically, that's the idea. This is going to be my solution. So y of x is this nice sum. So we've got an infinitely long polynomial that we're declaring to be the sum. Because I'm going to have to plug in for y double prime, let's kind of go through the paces here and talk about each little piece. Y prime would be the sum n goes from 1 to infinity of n a n x to the n minus 1. Remember, if you differentiate a power series, you take the derivative of the inside terms. So the derivative of x to the n is n x to the n minus 1. And then remember, you lose the constant term. So the constant term is a0 in this polynomial, and when you take the derivative, the constant term's derivative is 0. So that's why you have one less term in the differentiated series. Similarly, if I go all the way up to y double prime is the sum. N starts at 2 now. We lose another term. Go to infinity, we bring another power down. And so there are the pieces that I need. So this is always the first step when you do the series solution method. You assume that it's a power series expanded about an ordinary point. In this case, we will expand around singular points later. And then you have y prime and y double prime that you have to create here. So let me make sure that I'm giving myself plenty of room on this problem. It's going to be kind of a long problem, so I'm going to write sort of small. But the next step is then to plug these things into the original equation. When I do that, I replace the original equation here with the sum. N goes from 2 to infinity. And n minus 1. I'm simply copying this down at this point. And then plus y. And so y starts at 0 instead. And all that is equal to 0. The idea being here that this is a replacement for y double prime, and this is a replacement for y. Okay, so next step in the process is we do what's called a shift. We're going to shift the indices so that they start at the same value. I usually always shift to 0 if I can. So I'm going to shift the indices to start at 0. Remember the way that you do that, this one already begins at 0, so I'm not going to have to mess with it, but this one begins at 2. So remember what to do is if you subtract from the indice, you add to the variable, and if you add to the indice, you subtract from the variable. So they're opposite. So the idea here is if I want to start this sum at 0 instead, then I've subtracted 2 from the indices, so I have to add 2 to everything in the problem. So this n becomes n plus 2. This n minus 1, if I add 2 to it, becomes n plus 1. This a sub n becomes a sub n plus 2. That's extremely important. Every n in the problem goes up by 2. And then this x is now x to the n, if I add 2 to it. If you observe, I haven't changed the problem at all, and that's the beauty of this. I'm just doing some shifting to get things to line up right. If I plug in n equal to 0 here, I've got 2, 1, a, 2, x, 0. If I plug a 2 in here, I've got 2, 1, a, 2, x, 0. It's the exact same thing. So I'll bring this piece along as well. So now both of my sums are shifted to 0. And so because of that, I can write this as one sum. And then look at all the pieces or all the coefficients that I bring with it. So it's n plus 2, n plus 1, a n plus 2 plus a n. All of that's times x to the n. So basically all I'm doing here is I'm pulling out all of the x terms from my sum and looking at the coefficients that go with that. And so this is going to be equal to 0, which means one of two things. It means that either x is equal to 0, which is completely boring. We already know that y equal to 0 is the trivial solution. So if I want non-trivial answers, which I do, a non-trivial answer occurs whenever this coefficient becomes 0. So if I solve this for a n plus 2, which usually we solve for the largest coefficient present there, then this is minus a n over n plus 2, n plus 1, and this relationship is valid starting at 0, 1, 2, and so on, because my sum starts at 0, 1, 2, and so on. So this is one of the more important steps in this process. Getting to this point, this is called the recurrence relation for our solution. In other words, it basically says, if you can tell me what a certain value is of a, then I can give you the value 2 steps ahead of that. It's a recurrence relation. It relates new coefficients to past coefficients. This particular recurrence relationship goes from a sub n to a sub n plus 2, so it jumps 2 places, which means we call it a 2-step recurrence relation. Now, because of that, in order for this to work, notice that I'm going to have to know the values. So we must know the values of a0 and a1. And the reason is because it's jumping by 2. If I start at a0, in other words, if I know a sub 0, I can find a2. If I know a2, I can find a4. If I know a4, I can find a6, and so on. Well, what about a1, a3, a5, a7? Well, I need a place to start, and the starting place would be a1. So if I know a1, I could find a3. If I know a3, I can find a5, and so on. The point is, I must know a0 and a1, but we kind of already do know a0 and a1, or at least we have an idea of what they are. Notice that if I look here at the function y, then y at 0 is equal to a0. Similarly, if I look at y prime of 0, y prime of 0 is going to be equal to, or excuse me, y prime at 1 y prime at 1 is going to be equal to a1. So I know those values as long as I have this IVP that I'm solving. And so that's going to be a big part of this process, is we must have an IVP if we ever want to get a complete solution. But I'll show you, even if we assume we know A0 and A1, we can work the problem without having an IVP. All right, if I push this a little bit further, we want to solve for the coefficients. So I'll take this sort of one step at a time. We'll start with A0. A0 is equal to A0. I don't know what it is, but I'm assuming that it's a constant, which is a good assumption because it is. And then I'm looking at A2. So I'm using this recurrence relation. A2 would be when n is 0. That's equal to minus A0 over 2 times 1. A4 is minus A2 over 4 times 3. But I already know what A2 is. A2 is the same thing as minus A0 over 4, 3, 2, and 1, which is another way of saying A0 over 4 factorial. And similarly, if I looked at A6, A6 would be minus A4 over 6 times 5, which is the same thing as minus, I have A4 in the previous line, so it's minus A0 over 4 factorial times 6 times 5 is the same thing as 6 factorial. So what you see here is a pattern. Hopefully you can recognize the pattern. The pattern is, if my coefficients are even numbered, so A to n, it's equal to, well, notice that we get positive A0, negative A0, positive A0, negative A0, so we get a repetition here. So minus 1 to the n, we're getting plus or minus sign changes going on. A0 is the numerator, and the denominator is equal to whatever the term is. So A4 has 4 factorial, A6 has 6 factorial, A to n in general has 2n factorial. So we found one of the terms. Similarly, if I tried to calculate the other term, I would get A 2n plus 1 is equal to minus 1 to the n, A1 over 2n plus 1 factorial. So that would involve starting at A1 and then finding A3, A5, A7. Looking at a pattern, the pattern is all the odd coefficients will look like this. Now, if you put all this together, give myself a little bit of room here. If you put all this together, then basically what you have is my solution y of x is equal to, well, if you go back to what we called it, it's this power series expansion where I have ANs. Well, I've got different ANs here. I've got n goes from 0 to infinity. I've got one pair for the even coefficients, and I've got a different formula for the odd coefficients. Let's write out what they actually are. The even coefficients would be A0 sum n goes from 0 to infinity of minus 1 to the n over 2n factorial x to the 2n. And the odd coefficients would be minus 1 to the n over 2n plus 1 factorial x to the 2n plus 1. Now, this entire problem boils down to this last step, and that is, do I recognize these two power series that I've ended up with? And you hope the answer is yes, and in this case the answer is yes. The answer is I recognize the blue as being the power series expansion for the function cosine, and I recognize the yellow as being the power function expansion for sine. And so the final answer here, the final result is this is our solution. Our solution is exactly what it would be using this characteristic equation method that we've already described. Now I realize that is a very long process to come up with an answer. Are limited to having constant coefficients. We need to find a better method, and that better method is necessary to be able to do this series solutions method. Because we're going to look at a slightly more difficult this characteristic equation only works if we have constant coefficients. Please take notes over this. Please work through all of the pieces. I know I didn't show the work for a2n+1, but do that on your own and make sure you can come up with the same thing I did. All right, thank you for watching.